would notice it because our lungs wouldn't inflate when we tried to breathe. But how does this nitrogen get to be liquid nitrogen?
Hi, this is Lee Forsyth, and today I am going to host a watch party. This is a cryogenics demonstration done by Chuck Dieter here at the Headwater Science Center. It is 3:30 and it's our after-school STEM with a replay of a video that Chuck put together about a year ago. This shows some of those wonderful things you can do with liquid nitrogen at extremely cold temperatures. So I hope you enjoyed today's show. It is called Cryogenics, Chuck with Cryogenics Demonstration. Here it is.
In order to get it to be liquid nitrogen, you have to cool it down to at least 321 degrees below zero Fahrenheit. That's how cool it is in that cooler, 321 below. So we're going to use some of this liquid nitrogen, and it's a good way to approach some basic scientific ideas that have to do with energy, and how energy moves from one place to another, and what the three states of matter, solid, liquid, and gas, and what the difference is between those things. Now, of course, some of this is going to be review for a lot of you, you know these, but it's kind of fun to see the illustrations, and well, let's try with this. Let's take a look at this stuff. I better put my glasses on. There. Oops. Better. Not good, but better. Okay. Can you see it? It looks like water. It's a colorless, odorless liquid, and it looks like it's boiling. That's because it is boiling. It looks like boiling water right now. Now, why do you suppose that's happening? Well, we're going to talk about that. And well, you can see there's a little bit of wisp of something now and then. Let's take a look at that in a well, where it's plainer. Now I've got. Why is it boiling, by the way? Just poured it in there. Didn't heat it up. No heating source or anything there. Just poured it into the beaker. Good question to keep in mind. Now I've got some water in this plastic jug. And it's rapidly turning into a gas there. And above the water in the plastic jug, there's kind of a concentration of water vapor. You know, the water's always evaporating, so it's got water above it in the atmosphere above this. I'm going to pour some liquid nitrogen in there. Let's see what happens. We're getting low here. This is a fun thing we like to do with cryogenics demonstrations because we create this nice fog generator here. This is just fog coming out of here, and it's a flexible jug so we can play choo-choo train, and if you aim this carefully, we can make little fog rings. That's not our subject today. That's more along the lines of fluid dynamics. It could be we could make a pretty good demonstration about that. Anyway, that's a fun thing. Now, why is that happening? Why do we get all this fog all of a sudden, and it's coming out? We can put a little more liquid nitrogen in there, I suppose. And why is that happening? Kind of fun to play with. Now, let's get this out of the way for a second. Now, you've probably seen these before. Battery-powered decorative lights, Christmas lights, or whatever you want to decorate with them for. Now, what's going to happen if I put these batteries in that liquid nitrogen? What do you think would happen? Now, what's your experience with batteries in cold? Let's try it. That's one of the fun things about working at the Science Center. You get a chance to say, let's try it. We try things very carefully, and we try to predict scientifically and intelligently what's going to happen if we do something, but you still do get to try it. Sometimes you have to make sure you've got the right safety equipment with you. But let's see what happens. I'm going to just put those batteries in there. And I bet you a lot of you predicted that something's going to happen. my goodness. Getting a little dimmer. There they go. So, did we ruin the batteries? They're pretty cold. A lot of you encountered this, have encountered this when you go out and try to start your car in the morning at 30 below. Well, maybe we just ruined those things. Oh. Yeah. There we go. I'm gonna just set these over here like that. Nope. No, come here. There we go. Something like that. All right.
All right, so why did Chuck move those lights so that they would be in the camera? This is one of my favorite parts of this. Now you're going to want to listen and watch Chuck and find out all the other things he's going to tell you, but just keep an eye on those lights. Back to the show.
Okay, here's something else that's kind of fun. Here we have a piece of rubber tubing. Flexible, elastic. I've seen rubber tubing before. Now I'm going to put one end of the rubber tubing in there, in the liquid nitrogen. Excuse me. I have to stand up for this one. Now being careful. Oop. Well, okay. I'm going to pour a little liquid nitrogen into the tube. And of course it's boiling away. But eventually it's going down the tube. If I didn't have this glove on, my hand would be getting frostbite right now. It's getting pretty cold anyway. Active stuff. We'll see what effect these temperatures had on the rubber tube. Might have been pretty able to predict this, but you can see we've changed the properties of the rubber tubing considerably. Now, why did that happen? Anybody got any guesses? That's one thing we like to do. We like to ask lots of questions at the Science Center, and sometimes we come up with some answers, and sometimes we get people that make some educated and careful guesses that are actually pretty close to an explanation, a scientific explanation. But what's going on here? Why should that lose its elasticity? Why should it lose its flexibility? Now, we've seen it before. Uh-oh. Now, what's happening? Oh, no, I can't stay up, I can't. Stay up there. No? Not going to do it? Changing its properties again. Well, what's doing it? We didn't put it in something else. We didn't put it in, I don't know, do any changes to it. We just took it out of the container, took it out of the cooler. Well, I didn't have that on camera very well. Sorry. This is the first time we've tried to do one of these videos, and I'm using a laptop, just the laptop camera. So if we do more of these in the future, which we probably will, I hope we get some better cinematic equipment involved. But this is our first attempt right now.
Fun place to stop, because I'm going to tell you that since this video was created almost a year ago, we've done over 100 of these videos, and Chuck is right. We stopped using laptop cameras, and we stopped using our phones, and we invested in some pretty good photography equipment. And the content didn't change. The content stayed great because he's telling some great things today, but the filming really, really did improve after that. Still looking at those lights? Keep your eye on them. Here we are, back to the show.
Well, actually, we have had a couple other videos that had to do with snake feeding, things like that, just using a cell phone. Anyway, okay, let's do one more thing here, and then we'll talk about why these things are happening. Just take a look, we got a lettuce leaf here. What do you think will happen if I put this lettuce leaf in 321 below liquid? Let's give it a try. Now, one thing that we always remind people of when we do this in a demonstration is that all living matter, all living things, are made up of what we call cells. And you might have seen this in school, might have looked at things, living tissue or tissue from live samples under a microscope, and see that they're all made up of little tiny capsules, they're all divided into little tiny capsules called cells. And inside the cells is mostly water. So when you get it down to a cryogenic temperature, which doesn't take very long, it freezes. Now when that thaws out, it's not going to come back and just be like a lettuce leaf again. Because, well, one of the interesting properties of water is that as it gets colder and colder, like everything else, it expands a little bit. Not much, but a little bit. And that little bit of expansion is enough to break all the cell walls, all the walls to the, the outside envelope of the cell, the little capsule. And of course, when it thaws out and the ice melts, it's no longer a cell. It's just broken protoplasm, and it turns into kind of lettuce. This will turn into kind of lettuce slime, lettuce mush. And as a matter of fact, that's kind of what happens when you get frostbite, when your skin gets frostbitten. I mean, really frostbitten, so it's as white as this. The cells in your skin freeze, and the cell fluid inside expands and breaks the cell wall, and it can be pretty serious. That's a pretty serious injury. So take it seriously. Now, here's the question. Why did all these things happen? What made all these things happen? And here's the start of an answer. Just basic ideas. That's all we're going to go into. Let's see if we can see this. All right. I have here a cup full of wet sand. Don't need these right now. And I'm going to turn this over like this and pull the cup off. Ta-da! Science! Can you see that? It's just a cup shape. The point of this is, it looks pretty silly, right? When you do this. But the point of it is, it's a shape, it's a solid shape, and it's all made up of tiny little particles, grains of sand. Now the grains of sand, we can see them, and they're held together by water surface tension. Everything's like that in a way, okay? This is not, terribly complex or heavy science, but everything's like that in a way. It's a metaphor, you might say, in that everything is made up of little tiny particles. And some of you may know, of course, that the particles are much, much smaller, thousands of times smaller than those grains of sand, so you can't see them. You can't, even with a powerful microscope, you can't see them. But they're called atoms, if they're just one kind of particle, and or molecules, which are clumps of atoms. There are about 92 naturally occurring kinds of atoms out there. And so atoms that, say gold atoms, make up gold. Carbon atoms make up carbon. If you have a pure substance like that, silicon or manganese or whatever you're talking about, or nitrogen. Nitrogen is what we call an element. It's made up of one kind of particle. But if you, in order to get all the innumerable different kinds of substances there are out there in the universe, what happens is the atoms clump together in what we call molecules. You can have a 2-atom molecule like salt, sodium and chlorine, or you can have a 3-atom molecule like water, 2 atoms of hydrogen attached to an oxygen atom, or you can have 50,000 atoms in a molecule like some complex proteins. But atoms and molecules. So scientists have discovered that all things are made up of little tiny particles that we call atoms and molecules. Here's another thing that we found out. Let's pretend that these wooden balls I have in this tub here are atoms and molecules. And one thing that scientists have found out is the molecules always move. They're always vibrating. They're always shaking. Always bouncing against each other. Now, if they're held together, they're held together by charges, electron-sized charges. Now, electrons are particles that are, atoms are made up of subatomic particles, and some of those particles have a charge. A negative charge is, electrons have a negative charge, and protons have a positive charge. Now, the atoms and molecules are pretty much balanced, so they don't have, the whole atom doesn't have a charge, but the particles inside them have a charge. But that's not what's important here. The idea is that these are held together by electrical charges. You've got positive attracting negative, negative attracting positive. The opposite charges attract each other, and like charges, like two negatives, will repel each other. The point being that they're held together by electrical charges, and if the charges are really strong, and they're held really tightly together, even though they're vibrating, so they're really tightly held together, then the state of matter you're working with this, is a solid. Make sense? Sure, it makes sense. Now, let's say that you have some, the electrical charges holding them together aren't all that strong, or somehow you make them move farther apart, and they're still held together, but they're a lot looser, and they can flow more easily. That's called a liquid, right? Now, if you actually get these things moving fast enough and farther enough away from each other, so they're just... you have a gas. The difference between solid, liquid, and gas is the amount of energy, the amount of kinetic energy those molecules have when they're bouncing around. They bounce faster, they can be a gas. They bounce a little slower, they can turn into a liquid. They don't bounce much at all, but they're held tightly together, it's solid. Now, I think these are starting to come back. Now, all these things we've been doing, this is what's happening. Put that out of the way. Move this over here. Let's get one of these. Okay, this is the basic idea. You ever notice that, maybe it seems like when you have something cold against something warm, that the warm thing cools down, like you take take a can of pop or something and put it in the refrigerator, and it kind of seems like cold flows in to the pop and gets it cold. That's not really what's happening. What's happening is heat is flowing out. Heat always goes, that kind of energy always transfers. That heat energy is translated into molecular motion. The faster molecules are moving, the warmer something is. The slower molecules are moving in something, the colder it is. So how does one get transferred to the other? How does something lose its heat? Well, like this. Let's say you have something that's got slow-moving particles, which means it's colder, and it's moving nice and slowly, like that. But another molecule is in the area, and it happens to move faster. Molecule. Did you see how that happened? Okay, I'm going to start this one rolling really slow. This would be the colder molecule, and this is the hotter molecule. Now, if you look closely, you can see that when they collide, when the hotter molecule moves fast and hits the slower moving molecule, the slower moving molecule, whoops, let's get a little bit better than that. Slower moving molecule speeds up, the hotter moving molecule slows down. And that's what's happening with all of this. That's the whole process, that's the whole basic idea, is that faster moving molecules are banging into slower moving molecules and causing them to move faster. Okay, that happens with one molecule. Usually doesn't happen with one molecule at a time, it happens with millions of molecules at a time. And that transfers heat from something warmer to something colder. That's why we can say that there's no such thing as cold. It's not a something, it's a description. it means slower moving molecules. And something that's hot means faster moving molecules. You could say that the heat is a something because it's energy that's being transferred from one thing to another, and the cold is passive. It just kind of allows it to flow in. Well, let's take a look at this. The lights have come back on because the battery warmed up. What we did was, now, in order for a battery to produce an electrical current, there has to be a chemical reaction going on inside the battery. And that means that molecules have to be moving in order to interact with each other. When you slow them down so much that they can't move, they can't interact enough to cause a chemical reaction to move the electrons from one place to another to a great enough extent to light up the lights. But once they start warming up again, we didn't kill the battery, we didn't destroy the battery, we just cooled it down so that chemical reaction in there couldn't proceed. Now when it's starting to warm up, what's happening, of course, is the molecules in the air outside, the battery, are banging on this battery case, and they in turn are banging on the outside of the battery, and they in turn are banging on the molecules in the inside of the battery, and eventually that whole chain of reaction with molecules getting bounced from one place to another transfers heat energy into the battery, it warms up, and that chemical reaction has started again. And it'll light up the lights. And that's what happens when you're, trying to start your car at 30 below and it won't start, but if it, should get up a little bit warmer, and the battery warms up enough that the chemical reaction can take place fast enough and robustly enough to move electrons through the wires, then your car will start. When we poured liquid nitrogen into the beaker, the molecules of the glass of the beaker are moving a lot faster than the molecules of the liquid nitrogen, so as soon as they touch that, they get accelerated to the point where they get far enough apart from each other and they turn into a gas. They boil, which is what we're talking about with boiling. Boiling is changing from a liquid to a gas because the molecules start moving faster. With the rubber tubing, in order for the rubber tubing to be flexible and elastic, those molecules have to move. You slow those molecules down, and they can't move with relationship to each other, so it loses its elasticity and it loses its flexibility. But of course, when it starts to warm up, when the molecules of the air moving faster than these molecules intersect these, and those collisions start speeding the molecules of the rubber up, then it regains its properties. We didn't change anything, no chemical reaction involved. We changed its properties by changing the way its molecules move. Pretty simple, huh? And of course, that's what we talked about with the lettuce leaf. When the molecules of the water in here start banging against the molecules of liquid nitrogen, they give up their energy to those, and they slow way down until the water molecules collect together and attach to each other and form crystals. Now, the way that happens is fascinating, and that's an entirely different demonstration that we do called the unique properties of water. So maybe we'll do a video that has to do with those too. Now, this is just a good illustration when we're talking about how this happens. So I pour some liquid nitrogen into this flask. The molecules in the flask are moving much, much faster than liquid nitrogen. So they start turning the liquid nitrogen back into a gas. But now I poured just a tiny little bit of liquid nitrogen in there, tiny little volume, and I'm going to put a balloon on top here. We like to play with balloons a lot around here. And you can see how much farther apart these molecules are getting. Going from liquid to gas, tiny little volume of liquid, and it keeps building and building and building. Those molecules are so much farther apart. It's incredible that that little bit of liquid produces so much of volume. It's not even done yet. I'm going to pull this off. That tiny little volume would fit right down here at the bottom, and the space between the molecules is so great that it fills up this entire space, even against the tension of this balloon, creating pressure. And that's, of course, the basis of things like steam engines and all kinds of devices that use pressure that way. Okay, well, that's about enough messing around. So we tried some interesting things, had a little fun with changing the states of things and changing the properties of things and moving energy from one thing to another, all because molecules are transferring energy from one molecule to another just by banging into them. And that's a basic idea, okay? And if you start thinking about it, you can apply that to all kinds of things you see around you, even in the summertime, in the wintertime. Now, hopefully we'll do a few more of these demos, or not really demos, just videos about basic ideas. And that's enough. So, thanks for watching. Tune in to the...
I'll take it from there. Thanks for watching today. That was our 3:30 after school watch party. I'm going to let Chuck go now as we sign off. Thanks to Beltrami Electric Co-op. They have underwritten our shows with a generous donation. They sent us money so that we can continue to provide these shows for you at 3:30. There will be a show again tomorrow because we do this every single day at 3:30. So thanks for tuning in. Have a great day.